Okay, good morning, everybody again. So today we are to discuss or to continue our discussion of using integrals to compute the volumes of some solids of revolution. Um, can you confirm that in the lecture today you just finished some examples about the washer method but haven't gotten into the cylindrical shells method? Is that correct? Yeah. Let me see. When a lot, okay. Okay, great. So we still have time, so we don't have to hurry because I guess last time you already have seen both the cylindrical shells and the disc and the washer methods for a couple of examples we considered. So today we'll just continue on that, but I'll answer some of the questions your classmates sent. I think this is from the homework. So I hope you all will benefit with this discussion, at least to guide you with some of these problems. I won't answer all of them, but I'll show you the general process on how to do perhaps part of it and leave the similar portions of the solution to you. But if you have questions or clarifications, feel free to send them in the chat. So let me see. Okay. My screen is not showing up, but let me try it again. Okay, and so you guys can see my screen right now. Okay. We'll go here. Okay, the first question that was sent was about this. Just crop it up. Okay, so for this particular problem, we are given the solid was described in terms of its base and the cross sections that are used in order to get that solid, right? So again, I suggest you draw a rough picture of how the base looks like, and then try to use your imagination in picturing out how the 3D object was formed. So let me start with the base. So the base of the solid is bounded by y equals x squared and y equals 4. So y equals x squared is this parabola. Okay. And then the other boundary is the line y equals 4. Say this is a y equals 4, right? And then here we were told that the cross sections are perpendicular to the x-axis. So whenever your cross sections are perpendicular to the x-axis, then the variable that you will use in the integral will be the variable x, right? Again, if your cross sections are perpendicular to the x-axis, use dx. If it's perpendicular to the y-axis, then use dy, all right? Since the variable here is x, we need to bound x. What would be the bounds for x? Well, look at the shaded region. Figure out what is the x value, the starting x value, and what is the ending x value. So the starting x value is here, and the ending x value is over here. But these are the x coordinates of the points of intersection of the two graphs. So we need to solve for the POIs, points of intersection of the two curves, because they will tell us where when does the region start and when does it end, right? So let's look for those x values. So we just put those two expressions equal to each other. Remember, y equals x squared and y is equal to 4. So put them equal to each other. So we get x equals plus or minus 2. So here that's negative 2, here's positive 2, and then they will serve as the bounds for our integral, okay? And then the next thing is look at the cross sections. Imagine how the cross sections look like. Well, the cross sections are perpendicular to the x-axis, so they make a 90-degree angle with the x-axis. So therefore, cross sections look like this. Okay, they will be sitting on top of the of this region R, and then the shape constructing the solid will be going out of your screens, right? I guess last time we considered squares, we considered semicircles already. So if you have some difficulties on that, rewatch the lab meeting last time. If you have particular questions on it, then send them to the chat. But I'll focus on problem C, which says that the cross sections are equilateral triangles, right? So they are equilateral triangles. So imagine there would be triangles that are sticking out of the page. I hope you can imagine it. So you have the solid. This is the base on your screens, and then the cross sections would be triangles sitting on top of this region. All right. So that would be pointing out of your screens. So a bunch of those triangles, right? But remember, whenever you know the cross sections, the integrand will be the formula for the area of the cross sections. But the cross sections we have here are equilateral triangles. So we need a formula for the area of equilateral triangles. But the area of equilateral triangles, I did a quick check before going online. This is a square root of 3 over 4 side squared. Equilateral triangles, or all sides are equal. So if this is S units, this is also S units, this is also S units, right? So they are equilateral triangles. The area from geometry is the square root of 3 over 4 sides squared. So in order to figure out what's the formula of the area in the variable x, because remember our variable of integration is x, so the integrand should have the variable x. So we need to express this in terms of x. But looking at the figure, the side length is nothing more but the length of that vertical strip, right? Let me use a different color here. I simply need to measure that vertical strip because that vertical strip is basically the side length, right? And then how do we do this? You're getting there, Muriel. Just a little bit of an adjustment there. But remember how do we measure the height of a vertical strip? This is the same procedure we're doing for volumes, for areas, and so on. How do we measure the height of a vertical strip? Person, that's correct. You always do top minus bottom. So in order to measure a vertical strip, top minus bottom. So here, the top function is the red line, which is y equals 4. So I'll have a 4 minus the bottom function is the parabola with equation x squared. Okay, and this is the side length. That's the value of s. Plug in into the area of the equilateral triangle. It should be squared, then there should be a root 3 over 4 over there. And this will serve as our integrand. Okay? Is that clear? I hope that helped.
Thank you.
Right, so again, the crux here is first find the points of intersection that will give you the bounds for the integral. Second is look for the formula of the area of the cross sections. And then after you do that, solve for the corresponding parameter in the formula for the area. In this case, we need to find the side length, which turns out to be simply the height of the vertical strip that we drawn in the figure. And you see how important it is to have a clear picture of how the region looks like, how the cross sections look like relative to the base of the solid. Okay? Right. There's another interesting question, also from Michael. I'll go quickly on it. Guess that's the other problem. Okay, here. When is the deadline for this homework? Was it extended? Oops. Oh, it's Friday, so okay. And I see that most of you are already started doing it. I guess this is not a short homework, so because I guess this is number 57. Is the homework really that long? So I hope you guys have started working on it. If not, you should start getting to it. Yeah, I received about just 10 questions. I was surprised that the number was 57. But anyway, let's look at this one. So again, first step, have a solid picture or at least a rough sketch of the base. Well, the base is bounded by these two curves, x equals y squared. The first one is a parabola opening to the right. It's opening to the right because the squared variable is y. So the vertex is at y equals 0, but if y is equal to 0, x is also equal to 0. Okay, and then if y is equal to plus or minus 1, x is equal to 1. So I got that. There we go. So this is the first parabola with equation x equals y squared. Okay. And then the other one is this parabola, but let me rewrite it as x equals 3 minus 2y squared. The vertex is where? The vertex is at y equals 0, but if y is 0, then x is equal to 3. Let me use another color there. If y is 0, x is equal to 3. So I have that there. And then if y is equal to plus or minus 1, it happens that x is also equal to 1. I have these 2 points over there. And I was lucky that the points of intersection coincided with each other, right? Or I mean, I already see the points of intersection from the figure. I incidentally found them up um, by simply plotting the regions, right? But if you want to make sure that they are indeed the points of intersection, so you simply put the two expressions equal to each other. So we have y squared equals 3 minus 2y squared, okay? And then you have 3y squared equals 3, y squared equals 1, y equals plus or minus 1, okay? Then let's start working for the volume, okay? Now the volume now would be what? Well, look at the cross sections. The cross sections are said to be perpendicular to the y-axis. So we need to use the variable y because it's perpendicular to the y-axis. Then we need the bounds for y. This is our base. So here the shaded region started at y equals -1 and ended up at y equals +1. So they will serve as the bounds for our integral. Okay. And then next, let's look at the cross sections. Well, the cross sections are perpendicular to the y-axis. So for the cross sections, we have horizontal strips. And remember, horizontal strips always go with a dy, okay? There are 3 questions here. You use squares, you use semicircles, but I'll use rectangles with height h. So here, I'll answer part C. I'll leave A and B to you guys because that's similar to what we did last time. Okay, now we were told for part C that the cross sections are rectangles with height h. So here we have rectangles pointing out of the screen. Okay, so here this is h units. According to the problem, that's h units. It didn't give us the exact value of h, but treat h as a constant. All right. And then remember the formula for the area of a rectangle. The area of a rectangle is equal to length times width. In this particular case, we know that one of the dimensions has measure h. How about the other dimension? How long is it? So basically, we need to measure this, which is basically the length of our horizontal strip. But how long is the horizontal strip? Maria, you're correct. It's right minus left because you are measuring a horizontal strip, okay? So it's right minus left. The right function is what? The right function is the red one, which is 3 minus 2y squared. And then the left function is x equals y squared, so minus y squared. So that would be the area. So basically our integrand here would be the height times 3 minus 2y squared minus y squared. Or you could have simplified it as h times 3 minus 3y squared dy. Okay? I hope that's fine. Okay. Any clarificatory question before I go to the last question in the chat? Okay. I'll take your silence as a silence of type 1. Yeah, h is a constant. We just don't know its exact value. So you can just keep it there. Because, sorry, the difference here is that for rectangles, the height or the length is independent of the width. So there is no relation between this measurement and this measurement. That's why the problem gave us the value of one of the dimensions, because it is independent of the length of our horizontal strip. Yes, you can move it out of the integral. So your final answer, if you are evaluating this integral, your final answer will still have an h in it, right? Because h is a constant. We just don't know its exact value. Okay, now maybe 3 minutes for this last example from question from George. George is asking about problem 28, which is y equals cosine x, and y equals x plus 1, and x equals pi. Okay, so I suppose we need to find the area of this region. So in any case, we need to have a clear picture of how the graph looks like. Well, let's graph cosine. Cosine of 0 is what? Cosine of 0 is 1. And then cosine, what are the other special values for cosine? Cosine of pi over 2 is 0. Then cosine of pi is -1. So basically the cosine curve will look like that, right? From 0 to pi. And then the other function or the other curve is y equals x plus 1. So when x is 0, so for this guy, when x is 0, y is 1. And then if x is what? You can give any special value that you want. When x is equal to 1, which is over here, right? Pi over 2 is what? Approximately 1 point something. So 1 is here. When x is equal to 1, y is equal to 2. So basically, that's how the graph will look like. The line y equals x plus 1. And the third one is the line x equals pi. X equals pi is over here. X equals pi. Okay, so the shaded region should be the one bounded by these 3 curves altogether. So I guess it's now clear that the shaded region will be this one. Okay, and then since here the functions are given in the variable x, so perhaps it would be easier to integrate with respect to the variable x so that we don't have to compute for x in terms of y. First step is look for the bounds for x. Well, we know that the region started here at x equals 0 and ended up here at x equals pi. So the bounds would be from 0 to pi. And then since we're using dx, so the bound would be, or the integrand would be the length of a vertical strip. Okay, and again, I hope by now it's clear. We are repeating it over and over again. So I hope it's sticking to your minds how to measure the length of a vertical strip. It's top minus bottom, right? So the top function is x plus 1, and the bottom function is the cosine function. So that will be the integral that will give you the area of the shaded region. Okay, I hope that's clear. I hope this helps with your homework. Okay. Now I want you to remember these things because it seems that I am repeating myself over and over again, but I want to emphasize that point whenever measuring a vertical strip, top minus bottom. And then whenever measuring the length of a horizontal strip, right minus left. And that will be uniform in all the things that we do, right? For volumes, for other geometric objects. What's problem 58, Joseph? I don't think I have a problem 58. Did somebody send problem 58? Oh, it's the same as 57. Uh-huh. What's the exact question for 58? Oh, but perpendicular to the x-axis. So if that's the case, then all you need to do is, okay, so let me just copy this over. I assume you have the same region for that. Let me see. Okay. So if your cross sections are perpendicular to the x-axis, then the cross sections will look like this. Okay, so you will have vertical strips, right? Yes, you'll use vertical strips, but I guess you're right, Joseph. You will use two integrals because say you have cross sections that are semicircles, for instance. So for this semicircle, the area will be computed top minus bottom. So here you have x equals 3 minus y squared. Okay. Since you are using vertical strips, you solve for y in terms of x. So here you have y squared equals 3 minus x, y equals plus or minus root of 3 minus x. So whenever computing the length of this vertical strip, you will use root 3 of 3 minus x minus the bottom function, which is half of the parabola that you have. But the equation of that parabola is negative root of 3 minus x. So that would be the length of this vertical strip, right? Twice the root of 3 minus x, top minus bottom, right? But this semicircle involves this as your diameter, right? So you will use a different integral for this because the top function is half of the top half of the blue parabola, and the bottom function is the half of the blue parabola. But again, there you'll have y equals plus or minus root of x. So it would be root of x minus negative root of x. So basically, yeah, you're right, two integrals over there. Because the top and the bottom functions vary on two different intervals, right? And you will need to divide your integral along this line. You look at the points of intersection. Okay. All right. Okay, I hope that helped. Now, if there are no other further questions, then let's go ahead and go back to the examples we're working on in worksheet number 3. Oh, by the way, guys, I won't include the discussion or the solution I wrote for the homework problems in the annotated worksheet, right? So for you guys to be forced to write your own solutions to it. Okay, so let's go back here. Okay, so we were working on this example. I guess we did 15A and B. So let's go to 15C. Now, just to remind you, our equations here are the following. Here we have the blue curve is y equals 8x. And then the red curve is y equals x cubed. And for now, we are only you have only discussed disk or washer method in the lecture, so I'll stick to this method. We have another method which is called the cylindrical shells method, but you haven't discussed that in the lecture yet, so I don't want to preempt it. This worksheet is on my website. Go to the lab meetings channel, go to the top of the page. You see a tab there named Neil's website. Click on it and you will see annotated worksheet number 3. There's also a blank version if you want to solve it on your own. Okay. Okay, so we can only use disk or washer method. So again, whenever doing disk or washer method, the strips should be perpendicular to the AOR. Okay, that's the requirement. Disk or washer method always require the strips to be perpendicular to the AOR. In this particular problem, the AOR is the vertical line x equals 2 root 2. So this is our AOR over there. Okay. So that means to have a perpendicular strip to a vertical AOR, we need the strips to be horizontal, right? Or perhaps I should draw it somewhere here to illustrate it better. So we will use horizontal strips, okay? But notice that, okay, maybe I'll start here. So the volume would be an integral. Again, we are using horizontal strips. Horizontal strips always go with a variable y. So I have a dy there. I need the bounds for y. So look at the figure. What is the starting y value and the ending y value? So here, the region started at y equals 0 and ended up at y equals 16 root 2. So we get 0 here as lower bound and 16 root 2 as the upper bound. Okay? And then the integrand. What would be the integrand? Well, to know the integrand, we need to determine, is it a disk or is it a washer? What are the cross sections? Are there disks or washer? Now, how do you determine it? Well, remember I have drawn a horizontal strip earlier. So look at this. That's my horizontal strip. And if you look at that horizontal strip, part of it is outside of the shaded region. So what do I mean? If you look at this part, that is outside of the shaded region. Again, you draw a horizontal strip coming from the AOR towards the end of the region. But you see, part of that horizontal strip that I drew was outside of the shaded region. That tells me, oh, this is a washer, right? And for washers, the area of the cross sections would be pi times outer radius squared minus inner radius squared. Okay, that will go into the integral. So you can copy the pi over there right away, but we need to determine what's the outer and the inner radii. Okay, but I also remembered I'm integrating with respect to y. So that means I need to write the equation, the functions in terms of y. So remember, this guy can be rewritten as x equals y over 8. And then this can be rewritten as x equals cube root of y. Okay, because the integrand requires a variable y. Okay. Now, what is the outer radius? Well, the outer radius is the total length of the horizontal strip that I drew. So in this particular case, the outer radius will be this long. Okay, it's the length of the entire horizontal strip that I drew. So anybody, can you guess what's the length of that outer radius? That is measured from the AOR towards the endpoint of the region. Try again, Herson. It won't be 8x. And then remember, we are integrating with respect to y, so your answer should have the variable y in it. David, almost there. Muriel, almost there. You guys forgot how we measure a length of a horizontal strip? The length of a horizontal strip is right minus left. Remember, right? So what is the right function here? The right function is this guy, okay? The right function is 2 root 2. So that means this would be 2 root 2 minus the left function. The left function is y over 8. So that will be the outer radius squared. Remember, again, I'm measuring the length of a horizontal strip. It should be right minus left, okay? So that's the outer radius. So let me put a big grouping symbol here, and then I'll copy that 2 root 2 minus y over 8 quantity squared. Minus the inner radius. What is the inner radius? Well, the inner radius is the length of the strip that is outside of the shaded region. So in this particular case, this is my inner radius. Okay. Now, how long is that inner radius? I hope you now remember how to compute this. That would be what? Again, right minus left. The right function is 2 root 2. The left function is the parabola. Oh, sorry, not the parabola, but the red curve. And the equation of the red curve is cube root of y. Okay. So again, you always remember horizontal strips can be measured using the formula right minus left. It's a washer, so it's outer radius squared minus inner radius squared times pi. And then the outer radius refers to the entire length from the AOR towards the end of the region. Meanwhile, the inner radius pertains to the length of the strip that is outside of the shaded region. Okay, am I making sense here, or does it sound that I'm just blabbering over and over again the same phrases and not making any sense? Is it okay, guys, or are you still processing, digesting this information? Okay. Perhaps another example will make this clearer. For the next example, I'll use the same region again, okay, but a different AOR now. The AOR, or the axis of revolution, would be the line y equals -1. So the AOR will be somewhere here. Okay. So and then, so our AOR is horizontal. So we need vertical strips for the disk or washer method, right? Because again, the disk or washer method requires strips that are perpendicular to the AOR. So in this case, we will use vertical strips. And since we're using vertical strips, the variable of integration would be x. Okay, that's automatic. It's always x. Now, since the integral would be with respect to x, we expect two things. First, the bounds would be coming from the x-axis, right? So look at the region. The region started here when x is 0 and ended up when x is 2 root 2. So those would be my bounds, okay? And then the second thing is that the integrand should involve the variable x, since we're doing dx. Remember, the equation here is y equals 8x. And here this equation is y equals x cubed, right? And I expect these two functions to play a role in the integrand, okay? Now, is it a disk or a washer? What are the cross sections? Are they disks or washers? Well, if you draw a vertical strip coming from the AOR towards the end of the region, okay, you see that part of it lies outside of the shaded region, right? Specifically, this portion is part of the vertical strip, but outside of the shaded region. So this is a washer method. So for the washer method, again, it's pi times outer radius squared minus inner radius squared. Okay. Now, what's the outer radius? The outer radius is the entire length of the vertical strip coming from the AOR towards the endpoint of the region. So how long is that vertical strip? Try again, Joseph. Almost there. You forgot our fundamental concept. The length of vertical strips is computed as top minus bottom. So what is the top function? The top function is 8x. And the bottom is what? What's the bottom function? The bottom function is the AOR y equals -1. So basically the outer radius here would be 8x minus -1. Or that would be 8x plus 1. Is that clear? Again, it's top minus bottom. Top function, 8x. Bottom function, -1. 8x minus -1, or you can simplify it as 8x plus 1, quantity squared. That goes into your integrand. And then now, let's write the inner radius. The inner radius is the length of the strip outside of the shaded region. So the top function there is x cubed. Bottom function is -1. So again, I have x cubed minus -1, then quantity squared. Yeah, that's right, Harrison. The inner radius is x cubed minus -1. So your integral will have a minuend, or sorry, a subtrahend that is x cubed plus 1 quantity squared. Okay? Yeah, it is rotated about y equals -1. And you see how useful the picture was in this analysis, because now I'm thinking visually, right? Or I'm using this as a visual aid. So I always draw a strip. And then until now, even if I'm solving a problem for my research or for other more advanced things, I always go back to the basic, draw a quick picture, remember the fundamental concept, the length is always top minus bottom or right minus left. So this picture really aids me in setting up the integral that will give me the volume. And this will be helpful even if we go for surface area, if we go for the arc length, if we go to finding the centroid or the center of mass of your three-dimensional objects and so on. Okay? All right. Now, just a sneak peek to what will happen on Friday or what you will discuss on Friday. Remember the disc or the washer method always requires the strips to be perpendicular to the AOR. So we are bound to use only one strip. But there is an equivalent way of setting up the integral, but using strips that are parallel to the axis of revolution. So there's a way on how to set up the integral that will give the volume for this solid using horizontal strips. And that is the use of cylindrical shells. And you might notice in this set of notes, I have space reserved for the use of the cylindrical shells. It will use the other variable because it will use the other type of strips. Okay, any questions, clarifications? Okay, do you get it, guys? Are you still with me? Don't hesitate to ask questions if you have some. I won't take it against you. I really like students asking questions so that I at least have the chance to clarify what I had been saying the past half an hour or so. Okay, ready for problem 16? So problem 16. So here we have omega to be the region. Oh, before going that, nice question from Usosa. When should you do a y or an x integral? Well, it is always if you have a horizontal strip. Again, horizontal strips will require a y integral. Vertical strips require an x integral. Okay, so vertical, you use x. Horizontal strips, you use y. And that's always the case for whatever application. Be it area, be it volumes, be it surface area, be it the arc length that we will learn later, and so on. That's always the case. So it pays if you will remember that early on today. So you'll be used to it when we go to more advanced applications. Okay, let's try 16. So we have omega to be the region bounded by the curve y equals root x, x equals 0, and y equals 2. So let's start with the shaded region. Y equals root x, that's just a semi-parabola like this. And then y is equal to 2, somewhere over here. Okay, and then the x-axis is over here, or I should have used a different color here. That's y equals 2. And then the region is bounded by these two curves and x equals 0, which is over there. So this is my shaded region. Okay. And then the solid is formed by revolving this region about the line y equals 2. So this is also my axis of revolution. Okay. So, okay. And then let's set up the integral. Again, for now, we will be constrained for to use, sorry, let me do that here. Let's use disk or washer method. Okay. Now again, disk or washer method, the strips that you will use should be perpendicular to the AOR. The AOR is y equals 2, which is horizontal. So the strips to be used are vertical, right? So that means the integral will be an integral in x because I'm using vertical strips. Now the strips being vertical, we have dx, so we need to bound the variable x. I already knew that the region started at x equals 0, but it is not very obvious, or for some it might be, what is the ending x value? Well, that's just the point of intersection over there, right? So we just solve for the POI. If it's not too obvious, then solve for the POI. So we simply equate each other. So we know that y is equal to root x, and y is also equal to 2. So that means x is equal to 4. Okay, so the bounds would be from 0 to 4. And then remember, I need to decide, is it a disk or is it a washer? Or what are the cross sections, right? But if I draw a vertical strip from the AOR towards the end of the region, the entire strip is on the shaded region. There is no spillover into an unshaded part of the Cartesian plane. So that tells me this is a disk method, right? Or the cross sections are disks, because the entire vertical strip that I drew coming from the AOR towards the endpoint of the region lies entirely on the shaded region. And for the disk method, it is simply pi times the radius squared, right? So for a disk, you have pi radius squared. Now what's the radius? Well, the radius would be the length of the vertical strip. How long is that vertical strip? Anybody? So that I know that you're still listening. What's the radius? Don't be shy. There's no penalty for wrong answers. Yeah, that's correct, Herson. Top minus bottom. So that's going to be 2 minus root x. Right, Maria. That's all I did. Top minus bottom. The top curve is y equals 2. That's why I had the 2 here. The bottom function is root x. That's why I had the root x over there. Okay. At least I know that some of you guys are getting the hang of answering problems like this. That's why I think this worksheet is a nice exercise, though the functions given are sort of simple, but it gives you a different flavor when we put the axis of revolution from one place to another. All right, thank you. Good catch, Maria. That should be squared, right? Pi r squared. I usually tell my students that I'm doing those tiny mistakes on purpose so that I will know that people are still paying attention. So yeah. Okay. Right. Maybe we can finish the entire all the problems here in the worksheet as far as disk or washer method is concerned. Okay, let's try this problem. Problem 17. So again, we have a region omega bounded by the same curve. So basically, I guess we have the same graph as before, but the axis of revolution is different now. Oops. X-axis, y-axis, y equals root x there. And then the other one is y equals 2. Okay. Then we already knew this to be what? This was 4, x equals 4. And then this is the region omega. Okay. But now the axis of revolution is y equals 3. So this is our AOR y equals 3, right? So again, we can only use for now the disk or the washer method. The AOR is horizontal, so we will use vertical strips. So you draw a vertical strip from the AOR towards the end of the region. But Joseph is right. Look at the vertical strip that I just drew. A portion of it lies outside of omega. So that means this is a method of washers, right? But nevertheless, the integral will still be an integral in x since I'm using vertical strips. And the bounds would be the bounds for x. Omega started at x equals 0, and it ended up when x is equal to 4. So the bounds would be from 0 until 4. And then the integrand would be pi times outer radius squared minus the inner radius squared. Okay. Now, what is the outer radius? Again, the outer radius is the radius or the length of the entire vertical strip. How long is that? Again, it's top minus bottom. So remember, this is y equals 4. The black curve is y equals root x. So the outer radius would be 3 minus root x. Perfect, Arsalan. That's 3 minus root x. Quantity squared minus the inner radius. The inner radius would be this guy, the portion outside of the shaded region. That's right. It's this just one unit. Okay, because it's top minus bottom. That's 3 minus 2. That's 1. Or I guess visually you can see that because this is from y equals 2 to y equals 3. So definitely that's 1 unit. And that's it. That would be your integral. And then problem 18. Let's go to problem 18. If there are no questions with 17. Okay. Now for this, we have omega to be the region bounded by, I guess, these two parabolas. So let's see. Oops. Okay, the first one is, let me start with the easier one, y equals x squared. So that is just this parabola. Okay. The other parabola is y equals negative x squared plus 2x. The vertex, again, is at x equals negative b over 2a. B is the coefficient of x, so that's 2. A is the coefficient of x squared, so that's negative 1. So here we know that the vertex is at x equals 1. When x is equal to 1, then what would be y? That would be negative 1 plus 2, so that's going to be 1. Okay, luckily that's also equal to 1, so that's the vertex. And then, and then take 2 points, one to the left, one to the right of the vertex. Say when x is equal to 0, here we get y equals 0. So that's there. It's the first half of the parabola. Oops. And then when x is equal to 2, I will also get y equals 0 by symmetry. Or you can plug in x equals 2 in the equation. You get 0 for y. So the shaded region here is this. So this is omega. Okay. And then the AOR is what? What was the AOR? The AOR is the x-axis. So we revolve it around this guy. Right. Again, since we are using the disk or the washer method, we need strips that are perpendicular to the axis of revolution. So I will use vertical strips. But look at that vertical strip that I drew. Part of it is outside of the shaded region. So this is a method of washers. But nevertheless, the bounds will be bounds for x. We see here that x started at 0 and ended up when x is equal to 1. So the bounds would be from 0 until 1. And then since this is a method of washers, the integrand would be pi times outer radius squared minus inner radius squared. Okay. What's the outer radius? Outer radius is the length of the entire vertical strip. But again, that's top minus bottom. The top function is what? Negative x squared plus 2x, and the bottom function is y equals 0. Okay. Remember, the equation of the x-axis is y equals 0. Okay. So that's why we will have negative x squared plus 2x minus 0. Or you can just disregard the minus 0. Okay. How about the inner radius? Oops. Okay, let me just write it there. The outer radius, the inner radius would be this length. Again, top minus bottom, right? So the top function is x squared. Bottom function is 0, so it will just be an x squared. And I guess if you solve this, my note says it's pi over 3. So kindly double check that. For problem 17, double check it. It should be 8 pi. And for number 16, I guess this is 8 pi over 3. Let me check number 16, because in my notes, I also forgot to square the integrand. Okay, so let me just leave it like that. Okay. All right, I guess that's it for today, unless you have some follow-up questions. Okay, I will upload worksheet number 3 later, but I won't include the solutions to the problem, to the homework problems that you ask, right? Okay, right. I hope, Maria, that made sense. We're just running out of time and I have another class. If that's not clear still for you, just let me know on Friday or send me a message and we can have a tutorial tomorrow during my office hours, okay? So that's it for now, guys. Good luck on your homework and other submissions. Enjoy the rest of the day and see you again on Friday. Bye.